Happy Friday, everyone, and welcome back to our Back to Basics series. Today we're diving into the essential concept of unity gain in cable networks. Understanding unity gain is crucial for maintaining consistent signal strength from the head end to the end user, ensuring optimal network performance. In this episode, we'll demystify unity gain, exploring its significance in both forward and reverse paths, and discuss best practices for managing it effectively. I'm Brady Volpe, your host, founder of the Volpe firm, and Chief Product Officer at OpenVault. Joining us today is the esteemed Hranac, a veteran with extensive experience in the cable industry. Ron is a fellow member of the SCTE, co-founder and assistant board member of the SCTE's Rocky Mountain chapter, and an inductee into the SCTE Hall of Fame. His wealth of knowledge and experience is simply unmatched. Ron, it's great to have you here again. How's the signal level looking on your end today?
Great to be back, Brady, and thanks for having me here. And the signal level looks good, and yes, we're going to do a sort of a deep dive into the signal level aspects of what make up unity gain, and hopefully this will be some useful information that will help to clarify the principle of unity gain, which, as you noted, is crucial for ensuring really optimum cable network performance. And some people might ask, well, gee, does this still apply today in the world of HFC when, maybe it was more important back in the days of long amplifier cascades? And the answer is, well, yeah, it's still very important today. So that's going to be a lot of fun, I think.
Cool. So it's still needed, still relevant, and I think you have another great presentation for us to walk us through the importance of unity gain and how it works. So let's get that queued up, Ron. And for those in the chat, please do, if you have questions, drop us a question and we'll be sure to get on that. If you missed the chat, drop it in the comments below and we'll get back to you. All right, Ron, your presentation is visible.
All right. Well, as Brady said, and I reinforced, the topic of today's session is understanding unity gain. This is something that goes back decades in the cable industry, but still it can be a little bit confusing to try to understand and get your head around the concept of unity gain, and it can be even a bit more interesting in the return path, as you'll see here in just a little bit. So it's important to understand, of course, that the cable network performance is really kind of a balance between noise and distortion. This is true whether you've got a 30 amp trunk cascade or a node and a handful of amplifiers in cascade in a modern hybrid fiber coax network. The bottom line on this, of course, is if your signal levels in the network are too low, that can affect your carrier to noise ratio. And if they're too high, that can affect the carrier to distortion ratio. And really, you don't want to be below or above those thresholds where degraded carrier to noise ratio or degraded carrier to distortion ratio start to become problematic. Now, here's a really neat example of why this is important. This graphic is adapted from one in the book Modern Cable Television Technology, 2nd edition. And as you think about operating levels in a cable network, and by this I'm referring primarily to the amplifier or active device operating level. So it would be the output of a node would be included in that, as well as amplifiers going through a cascade. And as you look at this, you notice the horizontal axis varies from one amplifier over here at the axis or where the horizontal and vertical axes meet. And then there is no specific number on here because there's a lot of it depends that comes into play. But over on the far right side of this graphic, you see maximum possible amplifier cascade, and that goes up via that dashed line to this little sideways triangle. So think of the inside of this triangle as being the usable operating region where your network needs to be. And the optimum level would be this horizontal dashed line going through the middle of that triangle. And as you look at this, you'll see the upper edge of the triangle here refers to maximum output signal level. And if you exceed that, well, things start to get a little bit nasty because you get into the world of excessive distortions. And down on the bottom end of this triangle here, you have the minimum input signal level to an active device. And if you get below that, then things start to get a little gnarly because the carrier to noise ratio suffers and now you have excessive noise. So obviously, if you've only got one amplifier, I've got a pretty significant amount of wiggle room when it comes to signal levels. But the deeper you get in the cascade, the narrower that window gets. So that's an important point to understand, and really will point to the importance of unity gain. And I have a good example a little bit later on that shows what can go wrong when unity gain is amiss.
And just
Now,
touching on distortion and noise real briefly, Ron. So when I was starting in the cable industry over 30 years ago, distortion and noise were really important for analog signals, because they obviously would, distortion and noise would create a lot of different types of impairments that would impact picture quality. And one of my early mentors said that we live and die by CNR, carrier to noise ratio, when we're building RF amplifiers to optimize distortion and noise. Are distortion and noise still relevant when we are talking about QAM carriers and DOCSIS and things like that today? And we really don't have any analog channels.
Well, actually,
analog video channels.
Every one of those single carrier QAM channels and OFDM channels, they're analog. And you and I have talked about this before, and I love to give people grief about this and ask them, gee, do you carry any digital signals in your network? And everybody raised their hand. I said, no, you don't. Those are all analog signals. You got to convert digital signals to analog. So yes, as such, they are very susceptible to noise and distortion. So it's certainly important today. And on the bottom end, levels get too low, carrier to noise ratio suffers, and parameters like modulation error ratio, or MER, will suffer. And going up the other direction, if levels get too high, the distortions still become problematic, but they're not the composite distortions like we were used to seeing in analog networks.
CTB,
and by analog,
CSO.
Well, yeah, the composite triple beat and composite second order distortion. They don't have those clusters of discrete beats anymore. Instead, the distortions become noise-like. So now when you start cranking up levels, it looks like the carrier to noise ratio is getting worse. And you think, well, wait a minute, isn't that supposed to happen when you turn down the levels? Well, yeah, it does. But as you turn up the levels too high, then you'll see the carrier to noise ratio gets better to a point, and then all of a sudden it looks like the noise floor is increasing. That noise floor is actually a combination of thermal noise, but more substantially digital distortions or noise-like distortions. They're still there. Also, all the second and third order distortions don't go away. They just take on a different physical appearance as you're looking at them on a spectrum analyzer. And so it's still very important today. And as the industry expands operating bandwidths out to 1.2 gigahertz or 1.8 gigahertz or even beyond, it becomes even more important because those amplifiers are operating not that far from compression points. The total composite power coming out of modern amplifiers is pretty substantial. And if you don't manage the total composite power out of a given amplifier during operation, guess what? You'll start to degrade the modulation error ratio again. So yeah, it's very important. As we look back in history and talk about this concept that we're calling unity gain, it was discovered a long time ago, even way before I started in the industry in the early 70s, that for optimum performance of cascades of amplifiers, and understand back in those days, it wasn't unusual to see trunk cascades with 30, 40, 50, 60 plus amplifiers in a row. But the industry discovered early on that in a cascade of identical amplifiers, it was important to ensure that the gain of each amplifier in dB or decibels should be numerically equal to the combined coaxial cable and passive device loss in the span, and this is at the highest operating frequency, immediately upstream from that amplifier. And that principle is called unity gain. And as we've said a couple times already, it is still important in today's modern HFC networks, even as the fiber gets deeper and closer to the subscriber. As long as we've got any RF in our plant, we need to pay attention to this concept called unity gain. So importance is not going to go away until we get out of the world of coaxial cable and RF amplifiers in our business. So if we look at this from another perspective, and the concept of unity gain has to go all the way back to the design process. And it's not just operating and maintaining your network, but it goes all the way back to when the network is being designed on your base maps. So in a properly designed and a properly operating, and there's the operation and maintenance part of a cable network, the loss at the highest operating frequency in the coaxial cable and passives in the span immediately upstream from an amplifier location is exactly offset by the gain of the amplifier in dB, resulting in what's called unity or no net gain. So here's an example. I think that's probably all right. So here's an example. Let's say we've got 22 dB of combined cable and passive loss at 750 megahertz. I use that upper frequency limit in the examples in this presentation, but it applies if the network is 860 or 870 or a gigahertz or 1.2 gigahertz or 550 megahertz, 1.8. It doesn't matter. The concept is what is applicable here. So if we say this particular example here that I've circled in red, I've got 22 dB of combined cable and passive loss at 750 megahertz. And the amplifier immediately following that span has 22 dB of gain. So we say that the net gain, that is, there's no net gain, or it's unity gain. So in this case, for this span of cable and this amplifier, we say that unity gain exists for that span and amplifier. Now here's some other things, and this is where it can get a little bit tricky, but if we talk about forward path unity gain, and a lot of people might think, well, this is only important in the downstream. It's important in both directions, as we'll see. But when forward path unity gain exists, the input signal level to a given span of cable, so that would be over here on the left, so the RF input to this span of cable here, will equal the output signal level of the amplifier right down here immediately following that span of cable. Now, there are exceptions. And for those who've been in the industry a long time, you may recall that sometimes we would transition from a trunk bridge or amplifier to degraded line extenders, where there might be, let's say, 3 line extenders in Cascade or 4 line extenders in Cascade rather than 2. So then we would derate those line extenders. So that might be a type of exception you could see. But in this case, so we say the RF input signal level to this span, I'm calling it span N, between two actives, this value here should equal the RF output of the amplifier right here. I call this amplifier M, like Mike. So that's another example of when unity gain exists. So here's a cascade of 4 identical amplifiers. Now, in this case, unity gain exists in all of these, but here I've got span AB, span BC, span CD, and then amplifier A, amplifier B, amplifier C, and amplifier D. And as you look at this, you can see that the input to span AB, that's right here, this amplifier output, this A, which is the same as the input to the span, this one right here, this input level equals the output level of amplifier B. And that means then the input to span BC, this one, equals the output of amplifier C. And then, of course, amplifier C's output, which is the input to span CD, equals the output of amplifier D. Now, the assumption, of course, is we've got 4 identical amplifiers. And while it doesn't show on here, the line representing the span of cable could have splitters and directional couplers and other things in it too, but it's a combined passive and active loss in each of these spans between the active devices. Now, this also gets to what we call the unity gain reference point. Now, I'm going to come back to that a little bit later on, but as you look at this, you can start to think, where would the unity gain reference point be in this situation?
And also, the main reason you're trying to do this unity gain is going back to that very first slide, is we're trying to balance our carrier to noise versus our distortions in the plant. We're trying to optimize the signal quality of the signals that are going through those RF amplifiers, the coaxial cables, and also the taps and other devices that are going to be between those RF amplifiers. Is that correct?
Well, yes, it is. And that gets into a different part of system design and operation. And choosing tap levels or tap values and other things is a bit more complicated. And I'm not discussing that today, but primarily the combination of passive device and coaxial cable attenuation in that span need to equal numerically the gain of the amplifier following it. That's the important point about grasping unity gain, and really as the 30,000 foot view of what the heck is going on. Now, remember the graphic I showed earlier had the sideways triangle and that narrowing window. What can go wrong if unity gain doesn't exist? And I put this together. Let me slide this thing up here for right now. So I've got 10 amplifiers in Cascade, and the assumption is that these are identical amplifiers, and each amplifier has 22 dB of gain. However, for this example, I want to show how that narrowing window really becomes critical if unity gain isn't followed. But let's assume in this case the loss at the highest frequency between each amplifier is 23 dB instead of 22 dB. And you think, well, it's only 1 dB off. So what's going to happen? Well, let's take a look and see. So let's say the output of this first amplifier right here is 32 dBmV. Okay, so far so good. But with 23 dB of loss, the input to the second amplifier is going to be 9 dBmV. That's 32 minus 23 equals 9 dBmV. Now our second amplifier's output, because it's 22 dB of gain, you take the 22 and add 9 to it, so that means the output is 31 dBmV. And what does that mean?
Well, we'll just make up for that with a pad, Ron, right?
You can't. At this point, you're going to be a zero pad.
We don't have -1 pads?
Yeah, right. You're going to need them here. All right, so the input to the third amplifier is going to be, there's our output from the second amplifier, 31 minus 23 equals plus 8. Okay, so far so good. And the output's going to be plus 8 plus 22 equals 30 dBmV. Now, as we go through this cascade, remember, it's only the loss is only 1 dB less than the amplifier gain. By the time we get out here to the 10th amplifier, our input to that 10th amplifier is plus 1 dBmV, and the output is 23.
It's pretty low.
dBmV. And compare that to our first amplifier. The output was 32, but now we're down to 23. And there's nothing you can do to change that, because you've got amplifiers that have got a fixed gain of 22 dB. You can't increase that without replacing the amplifier. So at this point, you're probably going to be operating with 0 dB pads all the way through here. And I'm not even taking into account the insertion loss of equalizers. That really complicates things. But in this case, just not observing unity gain really trashes, in this case, the carrier to noise ratio as you go through the cascade. And by the time you get out here to the 10th amplifier, it's going to be pretty ugly looking.
Now, Ron, I think a lot of people would argue that there's not many cascades that are 10 amplifiers deep. We're like, we last week, John and I talked about node plus 6 is probably more typical. But I think you could argue that if you could be out at node plus 6, but after that you could feed maybe 1 or 2 line extenders after that 6th amplifier, or maybe even 3 line extenders after that 6th amplifier, and you would still now be at really what we call node plus 9.
Yeah.
It basically the same exact diagram that you just put up, and still be and have the same problem that you have. So getting padding and doing the padding right, starting at the first amplifier, is very critical. Even if you don't have that pad with you, it's important to go back or have someone bring you out the correct pad, because to your point, you can't make it up at the next amplifier. You don't have a -1 pad.
In this case, it doesn't matter if you've got a box full of pads, because your span loss exceeds the amplifier gain. You can't make that up.
It was a bad design to begin with.
It was a bad design. That's exactly what's going on. It was a bad design. And that's why I say the idea of unity gain goes all the way back to the design stage of the network. If you start out with a bad design, your network is going to not have ideal performance. If you've got 2 amplifiers after the node, all right, you might get away with it and it might be just fine. But if you've got 4, 5, or 6, things can get a little iffy, especially if the loss in the cable span is significantly greater by several dB than the gain of the amplifiers. So that's something to keep in mind. But then there's another piece, and I know you and John talked about, node plus 6 might be pretty typical, but I talked to cable operators and they say, well, yeah, that's what our design specs say, but we've got some cascades that have got 11 or 12 amps in cascade after the node. They have no choice, and unless they want to,
the reality of it.
Unless they want to run fiber out there someplace, and there's no way the company's going to pay for that. Now, maybe someday they will, but until that happens, they're stuck with these longer cascades in some cases.
Yeah, we'd love to hear how long your cascades as a cable operator Drop it in the comments below or drop it in the chat. Love to know what how long cascades are in the real world out there today.
Yeah, that's a good point. And I'll just throw this out there as a comment. The longest amplifier cascade I worked with, and this goes back to the late 70s, was a 60. The longest cascade was 67 amplifiers.
Holy cow, that's a long cascade, Ron.
I had a 12-channel system, thankfully, but just that was just awful to maintain. We had a full-time sweep tech who that's all he did was sweep plant to keep that reasonably decent with respect to performance. But you can imagine that things would look pretty gnarly after 67 amplifier. And anyway,
that's a full-time
job.
All right,
here's a diagram I'm going to use for the example of downstream unity gain, and I'll use the same diagram for upstream unity gain. So the same cable losses the same cable lengths and whatnot in between active devices, same passive loss and so on. So this is going to be, for this example, an example of downstream or forward path unity gain in a hypothetical 750 megahertz. Now, keep in mind, this same principle applies whether it's 550, 750, 860, or 870, a gig, 1.2 gig, 1.8 gig. Same principles apply. I just picked 750 megahertz because years ago when I first created this graphic, that's what I used, was 750 megahertz. And some of you may have seen this graphic in other presentations or publications. I don't remember when I created these graphics, but they have been reused by others over the years. I'm fine with that because it gets the concept across. So let's assume that for this example, in the downstream direction, we've got identical amplifiers, and that the gain is 22 dB for each forward path amplifier. And then we've got physical losses here. So you'll see I put it in meters, 452, call it roughly 453 meters between this amplifier and this amplifier. And then here we've got a directional coupler, and then 288.3 meters, and then this little span down here, 226.5 meters. And yes, some people will say, come on, Ron, why didn't you put that in feet?
you helped us out there. Thank you.
There it is. I put it on this slide, and that won't show up on the other slides, but if you don't like living in the metric world, there are the feet world right there. So there's your feet. So roughly just under 1,500 feet for span AB, span BC here, about 950 feet, just under 950 feet. And then span BD, just under 750 feet of cable. So let's see what we get. All right, the output of amplifier A, that's this first one, we're going to assume is 32 dBmV. And you'll see some of these numbers I used them on the earlier examples, but that means that the input to span AB is 32 dBmV. So output of amplifier A equals the input to span AB. So far, so good. Now, in this case, span AB is just a length of cable, roughly 1,500 feet of cable. And the loss through that length of cable is 22 dB at 750 megahertz. Now, this is going to give us 10 dBmV input to amplifier B. And that means then we're going to use a 0 dB attenuator here. Just to simplify things, I'm leaving out the insertion loss of equalizers. I just want to illustrate the concept. So here's where we are so far. So what we have then, remember the amplifiers have 22 dB of gain. And in this case, all the loss before this amplifier B is in the cable. So 22 dB of loss at 750 megahertz equals 22 dB of gain in that amplifier. So we now have unity gain in this scenario. And of course, as I mentioned, I've left out the insertion loss of equalizers just to simplify things. So in this first span, unity gain exists because 22 dB of loss in the cable equals 22 dB of gain in the amplifier. And then the 32 dBmV input to span AB, that's right here, is equal to amplifier B's 32 dBmV output.
Yep.
All right, now let's look at this next span. It gets a little more interesting because here we've got a combination of passive loss, the 2 dB through loss of the coupler, and coaxial cable loss. But in this case, we've got 2 dB of insertion loss on the coupler and 14 dB of loss in the cable at 750 megahertz. So 14 plus 2 equals 16. So that obviously doesn't equal the gain of amplifier C, which is 22. So what do we need? Well, we need a 6 dB input attenuator here at the input to this amplifier, because we've got 16 dBmV input. We need that down to 10. So we plug in a 6 dB input attenuator. Now, practically speaking, you've also got the equalizer loss. So the actual value of the attenuator is going to be a little bit different than what I show here. But this is, remember, this is just the high level view. So once we do this, now we have a total of 22 dB of loss in span BC. The 2 dB insertion loss in the coupler, 14 dB in the cable, and 6 dB in the attenuator here. So 6 plus 14 is 20, plus 2 dB here is 22. Now we have 22 dB of loss in span BC, which includes the input attenuator, and the amplifier gain is 22 dB. So here, unity gain exists.
Makes sense.
Now let's go to the little spur here, where we also have passive device loss. In this case, the down leg or the tap leg of the directional coupler has 8 dB of loss, and the cable, well, only 11 dB of loss there at 750 megahertz. So 11 plus 8 is 19 dB of loss. That means we need another 3 dB of loss via the input attenuator, because the input to amplifier D is 13 dBmV. So we plug in a 3 dB pad, and that gives us a total loss on this span of 8 for the directional coupler tap loss, 11 for the cable loss at 750 megahertz, and then 3 dB for the input attenuator. So 8 plus 11 plus 3 equals 22 dB. Now we have unity gain. And of course, span BD's 30 dBmV input, which is right here, because remember, we got to include that coupler, is equal to amplifier D's 32 dBmV output. And all this is predicated on the fact that we've got identical amplifiers. So far, so good. Now, let's get back to this thing I mentioned earlier, the unity gain reference point. But this example and the one that I had earlier really shows us where the unity gain reference point is. And in this case, it's the downstream amplifier output, or more accurately, or more specifically, or precisely, however you want to do it, the common point of the downstream diplex filter in this housing, which is typically on the downstream output side of the housing, which also usually, in most cases, now there's some exceptions, but in most cases, is also equal to the port of the output side in the downstream here. So there's our downstream reference point. Here, 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 and here. And one of our objectives when trying to achieve unity gain is to have the same signal level, 32 dBmV, at all of the unity gain reference points. So that's where they are on the downstream. Now, I just mentioned this, but I'll emphasize it in yellow here. Typically, the housing's downstream output port, or the common point of the output diplex filter. That's our downstream reference point for unity gain.
Okay. Ron, one question I want to, before you start, I know you're going to talk about the upstream. One thing you haven't mentioned when talking about the downstream with respect to unity gain is you've sort of always been talking about just one point of amplitude level. But typically in the downstream, we know anyone who's worked with RF amplifiers, the output of an amplifier has a tilted output. Is that something for maybe a later session that we want to talk about as to tilted output in RF amplifiers in a downstream?
Well, in this case, and maybe that's another topic for another time, but keep in mind our loss in the span is at 750 megahertz, the highest frequency. So 32 dBmV typically would be the highest frequency. So yes, you bring up a good point. It's not going to be a 32 dBmV flat output. It's going to be tilted with 32 dBmV, the highest frequency in use at 750 megahertz. And then 22 dB of loss at 750 megahertz here gives us 10 dBmV input here at 750 megahertz.
Okay. Very good.
And I'm trying to keep
it simple
at the 30,000 foot level, because practically speaking, you're also going to want to look at levels at lower frequencies too. But what we're doing here is defining the principle of unity gain
right
in the downstream.
Makes sense.
All right, now let's look at the upstream. Same graphic, same amplifier locations. We've got the same physical distance or amount of cable between active devices. We've got the same directional coupler here. But in this case, now we're talking about the upstream, where the assumption is all of the upstream amplifiers are identical. So we'll say that. And in this case, we're assuming that the amplifiers in the return path each have 15 dB of gain. So what that means is then what we want is 15 dB of loss at the highest frequency in the upstream to give us the principle of unity gain. But as you look at this first span here, what do you see? And again, remember the numerical gain in dB for the amplifier, which is 15 dB for these reverse amplifiers, should equal the combined loss of the cable and passives in a given span, immediately upstream from that amplifier. And you can also see where this might be going. So let's look at our unity gain reference points first. We already defined the unity gain reference points for the downstream. Well, guess what? The same physical location is where the upstream or return path unity gain reference points are. But in these instances, these aren't the outputs anymore. These are the inputs going the other direction. So here, the unity gain reference point and the return path is the input to each active device, which is the common point of that downstream output diplex filter, which is usually the same physical location as the housing's downstream output port. So guess what? That unity gain reference point in the reverse path is the same physical location as our downstream unity gain reference point. So that's another thing, and it helps to I think, simplify the concept when you understand that, gee, they're both in the same physical place. But one, in the downstream, it's the output. In the upstream, it's the input.
And a quick question here. You're using plus 20 dBmV as the input on the upstream for unity gain. I've heard different levels used by different people. Could be plus 17 dBmV, could be plus 18 dBmV, could be plus 20
plus
dBmV.
8, plus 10.
Is it really, really critical what that absolute level is, or is it just more important that you have consistency in the upstream when you're doing your unity gain balancing?
It all boils down to the system design. You have to go back to the system design. What upstream inputs are you designing for at your actives in the plant and at the node? In this case, I've chosen a design input of 20 dBmV for each of these upstream amplifiers.
Yes.
And I think could be plus 10, it could be plus 8, it could be plus 19. That's what I'm using for this example.
Yeah.
And that's going to give us some guidance then on where levels should be here and what we have to do. So once again, unity gain will exist when the signal level input to a given reverse amplifier, let's say right here, will equal the output from the span immediately upstream from that amplifier. So pretty straightforward stuff.
Yeah. And I'm really glad you mentioned the system design, because a lot of times people will ask me, well, what should my receive level be into my RF amplifier when they're doing balancing? It's like, I can't answer that question. No, I don't know how your system was designed.
That's right. You've got to check with your system. You've probably got some system design maps someplace that have all that information on them. And you look in the little tombstones, and all that information should be there, because you should be operating that network the way the system was designed.
Correct.
If you don't have that information, you're in a world of hurt, and you're going to be doing a lot of guessing. All right, so here we need, for this example, 15 dB of loss in each span to compensate for each amplifier's 15 dB of gain. So here we see that span AB, with this length of cable at 30 megahertz, it's a much lower frequency than our 750 megahertz downstream. We've only got 4 dB of loss in this span of cable in the return path. Now, I'm using 30 megahertz. Yes, it could be 42, could be 85, but I'm using 30 megahertz for this example. Now, interestingly then, in order to get unity gain, we have to install or insert another 11 dB of attenuation at the output of the upstream amplifier and amplifier B. Notice it doesn't get plugged in here at the input. We'll talk about that a little bit later on. It goes at the output
Right.
of amplifier B. This is the upstream output. So you plug in an 11 dB attenuator. So you got 11 plus 4 equals 15 dB of loss, in this case at 30 megahertz, equals the 15 dB of gain of that reverse amplifier. So now we have unity gain. So amplifier B's 20 dBmV input, that's over here, is equal to the 20 dBmV upstream output of span AB. That's right over here. So unity gain exists for this span that I've got circled in red. Now let's look at this. When we throw in some passive device attenuation, it can be a little bit trickier, but it's just a matter of adding these things together. So here we've got 2 dB of insertion loss on our coupler and 3 dB of cable loss. We've only got just under 300 meters here. So we've got 3 plus 2 equals 5 dB of cable and passive device loss in span BC. That means we need to install a 10 dB output attenuator here at the output of amplifier C. That's the upstream output. So then the numerical gain, 15 dB here, equals the total passive loss, 10 dB for the output attenuator, 3 dB for the cable, 2 dB for the through loss on our directional coupler. And as well, amplifier C's 20 dBmV input over here equals span BC's 20 dBmV output, which is right here, which also equals the input to amplifier B and so on. Unity gain exists. Now we move to here. Here, though, we've got only 2 dB of cable loss between this directional coupler and the next amplifier. So that says we've got 8 dB of passive loss. That's the tap leg of the directional coupler, plus 2 dB of cable loss is 10 dB. So if we need 15 dB of loss to have unity gain, we've got to plug in a 5 dB attenuator here at the output. And once again, unity gain exists.
So is this typically a two-man operation where you have one person at amplifier B and another person at amplifier D? The person at amplifier D measuring the incoming signal and the other person at the transmitting amplifier putting the padding in so that the person measuring the receiving signal can say, okay, you've put the proper padding in, so I'm getting the right receiving signal.
Well, you can make it a two-person operation, but these days, and actually for some time, the field meters that are used for aligning the plant or for sweeping or whatnot usually have what some people call an X-level test point up in the head end or hub site. And assuming unity gain exists, then what you're doing is your equipment, your sweep, let's say your sweep setup for a return path, and the same would apply in for the return path. You've got a gadget in the head end that's receiving your upstream sweep, and it's digitizing that and sending it downstream on a narrowband telemetry carrier. Your field meter is receiving that, and it's displaying what the equipment in the head end sees. Right. So you can make it a one-person setup and operation. Now, getting back to our unity gain reference points, the goal here is to have, again, for unity gain with this hypothetical design, you want to have identical signal levels at the unity gain reference points. And in these cases, in the return path, it's the input to the return amplifier. So and it's 20 dBmV at each point. So you've got that, and I've got them all circled, and you've got unity gain, which is pretty cool. But that's the basic concept of that. Now, earlier I mentioned that the attenuators are installed at the output. And that's true. And that's been true with two-way amplifiers for as long as I can remember. You might ask the question, well, why don't you put the attenuator, and if you're using equalizers in the return path, why don't you put them at the input to the return amp, like here, instead of the output or down here? Why can't you put them at the input? Well, if there was no branching in the network, which of course is nearly impossible these days, you're going to have branching and splits and whatnot. If there were no branching, you could do that. You could have the attenuator and equalizer here for the upstream. And actually that would work for this span because there are no splits or anything here. It's strictly cable loss. So you could hypothetically put an input attenuator here rather than an output attenuator here. But if span BD, this guy here, if the directional coupler wasn't there, you could also have an input pad here for the return path. But that ain't going to cut it because you've got branching going on here and you've got signals coming from two directions. So if you put an attenuator here at the return path input for amplifier B, that might compensate just fine for span BC, but it doesn't do anything. It's not the right value pad for span BD. So you can do one or the other, but you can't do it for both because you've only got one pad. That's why for two-way amplifiers and the reverse path amplifiers, the attenuator is installed at the output. So you want the correct total loss, say from here, including the output pad, through the cable, through the passive loss to get your desired input here. And because the cable loss and passive loss are different in span BD than they are in span BC, you need a different output attenuator to account for the total loss here.
Right.
So
if you didn't do it that way, you would have uneven upstream cable modem signals arriving at amplifier B. They wouldn't be the same level, and that would propagate through the rest of the plant, causing issues.
It'd be a mess. And just remember back to the example I gave with the 10 amplifier cascade where the span loss between amplifiers was only 1 dB worse than the gain of the amplifiers. Yeah. But look what happened to it by the time you got to the 10th amplifier. So imagine what kind of wonky things are going to, there's a high-tech term, are going to happen when you've got to accommodate the branching of the network, which is pretty true for most cable networks out there. So that's why
the CMTS would have a really rough time adjusting the levels of the modems if you had you did not have unity gain in the return. It would be really ugly. You don't want to go there.
No, you want unity gain. So we got through this material reasonably quickly, but hopefully it emphasized what unity gain is, why it applies to the downstream and the upstream, and why we want to do it. The reality is I'm going to call it a critically important principle that applies to both directions in our networks. And even in modern HFC networks that don't have very many amplifiers and cascade after the node. Now, obviously, node plus 0, well, there aren't any amplifiers to worry about after the node. But in most modern networks, the concept of unity gain still applies. And yes, you have to go all the way back to the design phase for your network to ensure that you have unity gain. And once you've got it built into the design, then when the cable network is constructed and first turned up, you want to make sure that it's aligned properly with unity gain concepts in mind. And then over time that you maintain the principle of unity gain by proper plant maintenance and troubleshooting. And if you don't have unity gain, your network performance will be impacted. Remember, if levels are too high, you start to run into the distortion ceiling. And if they're too low, you start to run into the noise floor. So carrier to distortion ratio gets bad if your levels are too high, and your carrier to noise ratio gets bad if your levels are too low. So it's an end-to-end process from design through installation and construction, maintenance, operation, and it'll always be that way till we don't have amplifiers in our networks anymore. And ideally, you really should try to ensure that your network is designed and built and operating with unity gain in mind. Now, are there some out there that don't? Almost certainly. Node plus 2 amplifiers, maybe it's not that big a deal, but I think in most cases it's going to be a very, very important principle to keep in mind. So with that, I'm open for questions.
Ron, with operators that are upgrading the return paths to 85 megahertz, or maybe even 204 megahertz, do you still see operators balancing unity gain in those frequencies? Or, as they expand to that, is unity gain still as important to balance in the return?
If not more so.
Yeah.
Yes, it is. And as you get into an expanded upstream, now you're dealing with a much wider RF bandwidth and signal levels that in some cases may be tilted coming out of the cable modem, because now you're trying to compensate for at least some tilt across the return path spectrum, because you're effectively dealing now with signals potentially from 5 megahertz to 200 plus megahertz if you've got a high split plant. And when I started in the business, the cable networks were 220 megahertz downstream. And so you think, well, all right, that's only from 54 to 216. Yet we had to pay attention to the idea of unity gain and signal levels and tilt and equalizers. Well, now just take that bandwidth and flip it around, and it's in the return path.
Right.
So yeah, you still got you've got loss, uneven attenuation through the cable, even over that narrower frequency range. So yes, it's critically important, even
Right.
Even as we migrate from subsplit to mid split to high split, and maybe someday ultra high split return paths. Very, very important to maintain the concept of unity gain to the extent possible.
So in your examples, you were showing of, kind of like doing the balancing or doing your test point, your test frequency at 30 megahertz. As you go to higher and higher frequencies in the return, would you recommend 30 megahertz to be the frequency that you use to be your test frequency
No,
for unity gain, or would that go to a higher frequency or maybe
it'd
multiple
be the highest
frequencies?
frequency, the highest upstream frequency, just like in the downstream, you're talking
Right.
about the highest downstream frequency. So yes, you want to make sure it's at the highest. Keep in mind, the example I used is just that. It's an example to show the concept or illustrate the concept. And it wasn't that. I mean, it seems like it wasn't that long ago, but really it was decades ago. We had 30 megahertz return paths, and then 40 megahertz and 42 and so on. But I picked a number for 30 megahertz, and I could have used 42 or 85 or something else. But yes, we've got to take into account the typically the highest frequency in the return path.
Yeah. And then I think the last question I have, and granted, for anyone else in the chat room has questions, please throw them in there. Smart amplifiers. So that's been an important topic that a lot of vendors are working on smart amplifiers that have equalizers, pads that are built into them, so they can ideally auto equalize, auto adapt the pads in them, either remotely or locally. How do you see that changing the way that we can manage, adjust, configure unity gain in both our forward and our return paths in the future?
Hopefully, and I assume that this will be the case, but hopefully those smart amplifiers will have built into their operation the idea of unity gain. And of course, the accuracy of the pad value, if it's all automatic, or the equalizer value, if it's all automatic, is going to be related to how accurately the smart amplifier is measuring signal levels. If a tech is doing this with let's say a smartphone or a tablet or something that's connected to the amplifier and then choosing those values that way, the tech needs to be aware of the concept of unity gain, and hopefully the network design will show that. Even if it's a smart amplifier, the network design should still show what the correct values are supposed to be. And I would think you'd want to at least check to make sure that the smart amplifier is indeed being smart about the choice of padding and equalization to achieve that goal of unity gain and overall optimum performance, whether it's downstream or upstream.
Excellent. All right, Ron, that was a great presentation on unity gain today. I feel like I have a much better understanding of unity gain, and I certainly hope our audience comes back with a much better understanding of unity gain. I think there are some opportunities for us to discuss things like, why we have tilted outputs in our amplifier, how DOCSIS 3.1 and even DOCSIS 4 even changes that more when we're going to have some stepped outputs in our amplifier. So there's things that we can talk about in the future when it comes to total composite power and things like that we have to look forward as DOCSIS continues to evolve.
Yeah, and it's not just DOCSIS. It's, yes, we may be carrying DOCSIS signals at those higher frequencies, but what if we carry some other kind of signal? Hard to say. I love the description that Glenn Jones, who owned Jones Intercable way back in the day. He's gone, may he rest in peace. But I remember him describing this back in the 80s, that a cable network could be thought of as an electronic pipeline. And what you put into it, that's up to you. Is it DOCSIS, analog TV channels, SC-QAM channels? It doesn't matter. And from the customer's perspective, they don't care. Is it all fiber? Is it fiber and coax? They don't care. It's still an electronic pipeline, and we've got to make that electronic pipeline work to deliver the best performance that it's capable of delivering. And a good part of that, at least when it comes to still having coaxial cable as part of the operation, is ensuring unity gain is kind of an underlying principle in everything, starting with design and going all the way through construction and operation, troubleshooting, maintenance.
Excellent. Well, we'll look forward to more discussions on that. Folks, we thank you in advance for subscribing and hitting the notification bell, giving us a thumbs up. It lets you know when we're bringing more content to you. A special thank you to Ron Hranac for sharing his extensive knowledge and experience with us today on Unity Gain in our Back to Basics topic. Ron, your expertise continues to be an invaluable resource to our community, so we really thank you. Join us December 13th for Ask Ron Anything Hour. We'll have tips.
Almost anything.
Almost anything, Ron. We'll have tips, tricks, and what not to do in your network hour. It's open format, so think of some good questions to ask us when we join you then.
And I do want to put some guardrails on that. If you've got DOCSIS questions, ask Brady and John. If you've got RF questions, you can ask me. I would suggest don't ask me product-specific questions. How do I set up brand ABC amplifier? Well, go look in the instruction manual. I'm not going to sit here and say, well, I don't know, where's the instruction manual for brand ABC amplifier? Go look in it. It should tell you how to set it up. But I would say those two constraints should be enough. And we can chat about stuff that perhaps has been covered in previous live streams that people may want a little bit more information on, or maybe something we haven't talked about, but all in this world of RF, the good old physical layer, because I am a PHY guy.
It's all PHY with Ron. Tom Ranson, thank you. He says, Ron, you're number one. So thanks for the feedback. All right. So, Ron, thank you again. Thank you for everyone in the chat room. Thanks for watching. Thanks for joining. We'll look forward to seeing you in our next session. We have 2 coming up in December. So until then, everyone, take care, stay curious, and keep watching. See y'all.